Okay, independence day 2. A lot of this, again, is just more examples. We've sort of seen these two rules already, but the addition rule for two events, remember, probability that E or F happens is the probability of E plus the probability of F minus the probability of E and F, so the overlap. If they're mutually exclusive, remember E and F usually equals 0. So that's like when you pick one card or you roll one die, that kind of thing. Multiplication comes in handy when you're doing more than one thing. So multiplication, the probability of E and F is the probability of E times the probability of F, given that E's already happened. Again, this is if you pick two cards. Now, if they're independent, this would just be E times F. But if they're not, like if I pick one card and I get a queen, oh, we'll get there, you'll see that the numbers will change. So given a deck of cards, what's the probability? I'm going to draw an ace or a king. So I'm going to use the first rule. So ace, there are 4 of them. King, there are 4 of them. There's no overlap because you can't be both. So, oops, 8 out of 52. So these are mutually exclusive. So 2/13. Given a deck of cards, what's the probability of drawing a red or a king? So red is half the cards. So 26 out of 52. King, there's 4 of them. But we're counting the king of diamonds and the king of hearts twice. So I'm going to subtract 2 of them. So 28 out of 52. So 7/13. So the multiplication rule would be like, what's the probability I get a king and then another king? Well, if I don't replace, there's 4 out of 52 kings to begin with, then there's 3 out of 51 kings the second time around, because these would be dependent events. So 0.0045. Now, if you were replacing the card each time, then they would be independent. It'd be 4 out of 52 times 4 out of 52. So just to like make sure we're organized with that. Here's another one. We're going to do a conditional probability with a tree diagram. It's been reported that based on a survey of 600 reformed and current smokers, that 11.3% of those who have attempted to quit smoking in the previous 2 years have used a nicotine aid. It has also been reported that 62% of those who quit smoking without a nicotine aid began smoking again within 2 weeks. And 60% of those who used a nicotine aid to begin smoking again within 2 weeks. If a smoker who is trying to quit smoking is selected at random, are the event selected smoker is trying to quit uses a nicotine aid and the selected smoker who is attempting to quit begins smoking again within 2 weeks, independent or dependent? A lot of words. Make a tree diagram. So, they either quit smoking with an aid or without an aid. So 11.3% have used an aid. So that means 88.7% did not use. Then they either smoked within 2 weeks or not. So those who used an aid, 60% smoked again within 2 weeks, so 40% did not. Without an aid, 62%, so 38. So we're trying to do independent. So again, our two independent rules. The probability of E given F should equal E, or the probability of E and F should equal E times F. Oops. I'm going to use this one because, first of all, we have a tree diagram, so it's easier to do a conditional. And this is the one that AP readers prefer. So, the probability given that they smoked again within 2 weeks, that they used an aid, should equal the probability that they used an aid in general. So this is the probability that they used an aid and they smoked again within 2 weeks over the probability that they smoked. It should equal 0.113 because that's the percentage of people who used an aid to quit smoking. So 0.113 times 0.6, so they used an aid and they smoked again within 2 weeks. There's 2 ways they could have smoked. They either used an aid or they did not. So, .0678 .61774. Actually, this should equal 0.113. It's 0.1078. Oh, sorry, 98. Oh, wait, I did that wrong. Oh, no, I didn't. I rounded wrong. Let's look at the numbers here real quick. So, when I round this is 10.9%. So I should round up, right? So 11%. Now, 11% to 11.3% is close. Again, this is the one case where we're using a sample. So here we can say, yes, they are independent. It's close enough with some sampling variability. So you need to be careful when you're looking at samples here. The numbers can be close enough, not exact. So here 11% and 11.3%, that's why they were close enough. You could try and use this other one and see if it gets close. I'm assuming you're going to get the same answer. So on the back, let's try another one. Assume there's a certain test for cancer is 98% accurate, by which we mean if the test is administered to 100 people with cancer, that it will detect the cancer in 98 of them. If it's administered to 100 people without cancer, it will show 98% of them free of cancer. Assume this test is given to 10,000 people, half of 1% of whom actually has cancer. If Mr. Test Case is one of those people who's told that he has cancer, what's the probability he actually does have cancer? So again, make a tree diagram. So they either have cancer or they don't. Again, it's a super small percentage. Half of a percent, so 0.005. So 0.995 don't have cancer. Then we have a 98% accurate test. So 0.02, 0.98. So, Mr. Test Case, we're going to look, what's the probability he has cancer given that he tests positive? So we're going to look, that means that he should have cancer and test positive over the different ways to test positive. I don't know why I put post, but you get the idea. So, has cancer and he tests positive, 0.005 over 0.98, over the 2 ways to test positive, 0.005, 0.98, or he cannot have the cancer and get a false positive. .0049 .0248. So if I divide them, I get 0.1976. So 19% chance that he actually does have cancer. Now a lot of people will ask, well, why is this so small? Like, if it's 98% accurate, he should have a higher probability of having cancer given that he tests positive. The problem is that this cancer is so rare that it's really weighting your average down. So that's why it's such a small probability. Okay, so just a few things to go over. Again, making sure that you know your independent rules, kind of looking at our general rules for one event versus two events. Nothing new today, just kind of more examples.